Ever wanted to experience room-shaking, high-fidelity sound from speakers you built yourself? Today, I'm taking you through a DIY tower speaker build that looks stunning and sounds even better. From cabinet design to high-fidelity crossovers, I'm breaking it all down. Ready to turn raw materials into pure sonic power? Let's get started. Materials and components, the foundation of any great speaker build. Let's break it down, starting with the cabinet. So for the cabinet material, you want something with good density to minimize unwanted resonance. I'm going with 3/4 inch MDF. It's solid, reliable, and widely used in speaker construction. But hey, you do you. Choose what fits your vision. So let's talk about the real stars, the drivers. I'm using Dayton Audio drivers. These strike a great balance between quality and affordability. Now, if you want to step it up a notch, check out brands like CSS or SEAS for some really high-end options. For high frequencies, I'm using a large air motion transformer tweeter. This has quickly become one of my favorite tweeter designs. I do a lot of critical listening on my Atom AX7 monitors, and compared to traditional dome tweeters, the AMTs offer incredible detail with minimal ear fatigue. Trust me, once you hear them, it's really hard to go back. Now, handling the mids and the lows, we've got Dayton Audio's paper cone reference drivers. Paper cones are known for their smooth response across the frequency spectrum. Unlike rigid composite materials, they naturally minimize the ringing in the top end, resulting in a more balanced and natural sound. Now let's talk about the speaker crossover. This is the electrical circuit that directs specific frequency ranges to each driver, ensuring a balanced, controlled response. Now, skimping on quality here can lead to a smearing of details and a distorted sound stage, so it's critical to use high-quality components. A typical crossover is built using three main components: inductors, capacitors, and resistors. I'll break down my crossover design later in the video, but for now, here's what I'm working with. For inductors, I'm using air core inductors. If you have the space, an air core inductor is the way to go. Now on the capacitor side, I'm using Dayton Audio's metallized polypropylene caps. These handle high voltages really well and don't degrade over time like their electrolytic capacitor counterparts. And they also offer low distortion and excellent accuracy, which makes them perfect for high fidelity audio. Lastly, for resistors, I'm using metal oxide non-inductive resistors. These are ideal for speaker crossovers because they provide stable, low distortion resistance without adding unwanted inductance into the circuit. All right, let's talk design. Because great sound starts with smart engineering, I put a lot of thought into the shape and structure of this tower. So let's break it down. The tower stands at 40¼ inches tall, 13½ inches deep, and 7½ inches wide. These dimensions aren't random. They're dictated by the internal transmission line. Inside, we've got a folded chamber that matches the woofer's diameter in depth and stretches out to a full 72 inches in length. If you're wondering how that works, don't worry. I'll do a deep dive on the transmission line later in the video. No, lie down, Benny. Lie down. Now at the bottom, we've got the port and the 4 feet to elevate the speaker. This not only gives it a clean, modern stance, but also helps with airflow and sound dispersion. Now on the outside, I went with a matte black paint job with decorative stained side panels. Clean, simple, and sharp. But because I couldn't resist, I threw in an LED strip up the middle. Because why the f not? So that's the design in a nutshell. Now, let's get into the build. Before we dive in, quick PSA. MDF dust is nasty stuff. Seriously, wear your PPE. You don't want to be breathing this stuff in. First up, we're cutting the exterior panels. The bottom plate, which supports the entire speaker, measures 7 inches wide by 13 3/4 inches deep. The top panel mirrors that exactly. The front baffle and the back panel are both 37 1/4 inches tall by 7 inches wide, while the side panels are 37 1/4 inches tall by 12 1/2 inches deep. Next, I cut a 3 1/2 inch porthole in the bottom plate using a hole saw. Now, to help with airflow, I round over the edges. A small detail, but it makes a difference. Now, to ensure a strong, airtight seal during assembly, I cut an 1/8 inch slot all around the top and bottom panels, as well as along the sides of the back and front baffle. I do this with a 3/4 inch bit on the router table. This helps everything fit together cleanly when we start gluing up. Now here comes the nerve-wracking part. Cutting the driver openings. Precision is key here. For the tweeter, flush mounting is super important. If the high frequencies hit sharp edges, they can diffract and create unwanted artifacts in the sound. For round drivers, a circle jig makes this easy, but with a rectangular AMT tweeter, things get trickier. Now, to get the perfect cut, I built this custom router jig. It wasn't too difficult, and I'll drop a link below on how you can make one. The key is using a router bit that matches the corner radius of the tweeter for a perfect fit. For the woofers, the process is more straightforward. Using a router jig, first I use a bit that matches the depth of the woofer support ring, cutting just deep enough to let the driver sit flush. Then I remove the inner material with a straight cut bit to complete the cutout. One important step here is rounding over the inside edges of the woofer cutout. So last bit of cutting, we carve out a channel for the LED strip. Similar to the tweeter, I built a jig specifically for this to match the exact dimensions of the LED diffuser channel. Before assembling the cabinet, I cut the interior panels that form the transmission line. The long panel is a piece of 1/2 inch MDF cut to 25 1/8 inches long by 5 1/2 inches wide. The horizontal section is 3/4 inch MDF cut to 5 1/2 by 5 7/8 inches. One thing I forgot is cutting out the hole for the speaker binding posts and plate. No big deal. It's easy to drill out and cut out this section after the fact. Now it's time to put it all together. I go heavy on the glue. Probably a little excessive, but I'd much rather have a rock solid seal. Cleanup is easy once it dries. I glue up the cabinet in stages, letting each section dry for at least 4 hours, sometimes a full 24 hours, just to be safe. And don't skimp on clamps. The tighter the seams, the better the build. Time for some fun. LEDs. I'm using a warm white 12-volt LED strip in a diffuser channel to create a seamless light source. I start by installing the aluminum LED channel in the front baffle cutout. A grinding disc works great for trimming these to size. Once it's in, I drill a small hole through the bottom of the channel into the cabinet for the wiring. So here's a tiny tip. When you buy LED strips, they usually have pre-soldered wires on both ends. If you cut the strip from each end of the roll, you can use the existing wires to extend your connection, so no need to solder new leads directly on the LED strips. On the back of the cabinet, I install a female 12-volt adapter inlet mounted to a small MDF disc. Once the wiring is in place, I seal everything up with caulking. And just like that, LEDs on a speaker. Now that this part of the cabinet is assembled, it's time to add the finishing interior touches. First, I cover the bottom port using a vacuum filter cut to size and then stapled in place. For internal damping, there's room to experiment. I've had great results with 2-inch high-density foam, so that's what I'm using here. I shape the foam to fit around the woofers, ports, and other internals. Then I secure it all with foam adhesive. So at this stage of the build, I think it's a great time to explain how the transmission line works. Now the drivers I'm using have a resonant frequency of 47.1 Hertz. This is the frequency where the driver operates most efficiently, meaning that the diaphragm moves the most with the least amount of resistance. However, in free air, the driver struggles to produce those lower frequencies as loudly as the ones above that range. This is where the transmission line comes in. Engineers discovered that if you build a dampened chamber inside the cabinet with a length equivalent to 1/4 of the wavelength of the driver's FS, the pressure inside the chamber will reinforce those lower frequencies. Additionally, by lining the path with absorption material, you can filter out unwanted high frequencies, leaving mostly low-end energy escaping through the vent. Now, a common misconception is that sound waves are traveling directly from the back of the drivers down the transmission line and then out the vent like a horn. That might lead some of you to wonder why my vent is at the bottom and not at the end of the transmission line. But what's actually happening here is that the driver's movement is altering the pressure within inside the entire chamber. This means that no matter where you place that vent, the same low frequencies from the transmission line will still be present. So I position the vent at the bottom because it maximized the phase alignment with the sound coming off of the front of the drivers. Now, when I placed the vent on the front, the output was out of phase and canceled out the frequencies below the driver's FS. I also tried putting the vent on the back, which gave me a similar result. But when I placed the vent on the bottom, it was like adding a subwoofer. It reinforced the low end instead of canceling it out. If you're enjoying the build so far, drop a like and subscribe. Got any pro tips for speaker builds? Let me know in the comments. I'd love to hear what techniques you use. Now that the interior is complete, we can finally close up the cabinet. First, I add foam to the side panels for extra damping, then glue them in place, sealing up the enclosure for good. Before we move on to the finishings, I need to clean everything up. I start by sanding the cabinet to remove any of the dried glue and smooth out the surfaces. Once that's done, I use a 1/2-inch roundover bit to round over all the edges. This not only makes the speaker look more polished, but also helps reduce diffractions, keeping the sound clean. Since I'll be gluing on the side panels later, I tape off those areas to avoid getting too much paint where the glue needs to bond. Now we're ready for paint. Well, almost. MDF is a tricky material to paint. The edges are super absorbent, and if they take on too much moisture, they can swell. Definitely not what we want. To prevent that, I seal everything with a shellac-based primer. For the main finish, I'm using spray paint. It gives the smoothest finish and helps avoid brush strokes. If you want a pro level look, multiple coats are key. I sand between each one for that perfect finish. For the side panels, I cut them to 37 inches by 12 inches, leaving about 1 inch of the interior cabinet exposed all around. Then I round out the corners on the bandsaw and use a router to soften the edges. For the stain, I'm using a penetrating oil-based wood stain in the color of Puritan Pine. Once it's dry, I remove the masking tape from the cabinet, glue the side panels in place, and then add a few nails for extra hold. For the speaker feet, I cut out 2.5-inch circles using a hole saw. Then round them over by securing them to a board with a nailer and using the hand router. Once they're shaped, I hit them with black spray paint and they're ready to go. Now that the entire cabinet is built, it's time for protection. I apply several coats of polyurethane wood finish to lock everything in and give it a smooth, durable surface. Like with the paint, I sand between coats to get that perfect silky finish. So we start by positioning the drivers in place and marking out the mounting holes. Once that's done, we pre-drill the holes to make installation easier and avoid any unwanted damage. For the internal wiring, I'm soldering the speaker cables directly to the drivers. Now you can use slide-on clips for convenience, but soldering ensures the best signal transmission. Now on the back of the speaker, I've gone with a 2-way 4-post terminal setup. This gives me flexibility for wiring and future-proofs the design in case I ever want to experiment with bi-amping. Now when choosing terminals, avoid anything that uses magnetic metals, as they can impact signal quality. Often you'll see brass terminals, but they come with steel nuts. No bueno. I'm using all brass terminals with brass nuts that have a silver coating. All right, let's talk about one of the most critical aspects of this DIY speaker build, the crossover design. For this build, I went with a 2.5-way crossover design. Unlike a traditional 2-way design, the 2.5-way approach applies an additional low-pass filter on the lowest woofer in the array. This helps shift the acoustic center higher on the speaker, improving off-axis response and minimizing phase issues as you move vertically. Now, since both woofers share the same low-frequency signal, it's not quite a 3-way system, but it enhances overall coherence and imaging. So before diving into physical assembly, I started by modeling out the crossover using XSIM, a powerful crossover design tool. Got the link below. This software lets you simulate how the drivers will interact based on their factory specifications. Now, while it doesn't account for cabinet effects or driver positioning, it provides a solid foundation for an efficient and optimized crossover design. Once the speakers were constructed, I moved on to real-world measurements using REW, Room EQ Wizard, a free acoustic measurement tool. This process involves playing test signals through the speakers while capturing their response with a calibrated measurement microphone, positioned 1 meter on axis from each driver. These measurements replace the factory specifications in XSIM, allowing for a more accurate crossover design that accounts for cabinet resonances and driver placement. It's important to note that after I did these measurements, I realized that because my tweeter was in the same plane as the woofers, the driver elements are positioned differently, so I was probably going to need to swap the phase on that tweeter to help with phase alignment. So looking at the components, the AMT tweeter naturally rolls off around 2000 Hz and has a boost above 8 kHz. Now to cut off the bottom frequencies, I used a second order 12 dB per octave high pass filter. To do this, you start with a capacitor in series for the high pass filtering. And then after that, you add a parallel inductor for further attenuation of the unwanted frequencies. And then a resistor to fine-tune the output to match the level of the woofers. Now the woofer circuit follows a similar approach but in reverse. So I started with an inductor in series to create the low pass filter and then added a parallel capacitor to further smooth out the roll off. Then I added the extra inductor so we don't have too much high end playing off of that lower woofer. Once the crossover modeling is complete, I moved on to real-world testing, swapping out components, fine-tuning values, and dialing in the exact voicing that I wanted. Now originally, I planned to mount the crossover inside the speaker cabinets, and I even built a mounting plate so I could do this. But I decided to take a different approach, an external crossover display for the two-way section of the crossover. Not only does this make component swaps easier, but it also looks really cool. So for the construction, I used a 1/4 inch piece of MDF painted black for a really cool, clean aesthetic, and then marked areas to drill holes so I could run zip ties through to secure the components and also run their connector leads down through the board for soldering underneath. And then for final presentation, I built this box that would hold the crossover in place, and I put a plexiglass top over it so the crossover itself is fully visible. Then I added speaker terminals on the input side and on the output side for the appropriate connections to the speakers and from my amplifier. So the only part left is the additional low pass filter on that lower woofer. Because this is made up of a large 2 millihenry inductor, I figured I would take advantage of the fact that I already had a mounting plate inside the speaker and put it on its own board. Now, if inductors are placed too closely together, you can actually get crosstalk if you don't get the positioning right. So there's actually an advantage here by separating it from the two-way. Also, the other thing to consider is that I would need a 3-way binding post setup on the back of the speaker if I had it externally. So it's kind of a win-win. All right, let's have some fun. Now, before we dive in, let's acknowledge the obvious. Translating an in-room listening experience through microphones to your ears is far from perfect. Plus, looking at speaker measurements doesn't tell you much about the soundstage or overall character of a speaker. But hey, we're gonna do it anyways, because why not? So for this test, we'll compare a section of music across 4 different sets of speakers. So set 1, Atom AX7 monitors. This is a bookshelf monitor with an AMT tweeter and a flat, accurate response. Set 2 are Klipsch Reference Premier Towers. These have dual 5-inch woofers and a much livelier top end. Set 3, Klipsch RF62s, a larger, older model with really good low-end presence. And finally, my DIY CFSTL26s. My custom build, which I'm really excited to put to the test. So to capture the sound, I'm using a pair of Aston Origin large diaphragm condensers, panned left and right. The speakers, except for the Atoms, are driven by a Yamaha receiver set to pure direct mode. For measurements, I'm using a Sound Devices test mic with REW software. All right, let's start by listening. I'm gonna switch between all the speakers so you can hear the differences. Let's go. Now let's look at some on-axis frequency response measurements. So with the Atom A7X, we see a slight lift in the highs, then relatively flat until those room modes start interfering. Then once it hits 50 Hertz, it's game over. Now with the Klipsch Reference Premier, we see a much different response. There's a lot stronger top end presence, and you see a deeper bass extension, plus some peaks and dips due to the room. Now with the CFSTL26, it's a little flatter than the Reference Premiers, but still quite similar overall. And with the Klipsch RF62, as expected, it dominates across the range. And here they all are side by side. It's quite a party. So what does all this tell us? Well, the CFSTL26s measure like a typical consumer speaker. In a room you can't fully trust. Using a process you can't fully trust. But trust me, they sound fantastic. And at the end of the day, I built them myself, which is something money cannot buy. Though, I did have to buy all the parts. I hope you enjoyed this video as much as I enjoyed making it, and I hope you were inspired. Please drop a like, subscribe, and let me know what you'd build next. We'll see you on the next one.